Somebody needs to remind me to turn this off when we go to lunch. I know it's not before that. All right, so let's review the properties of logarithms real quick. Okay, I'll write the property, and you'll finish it for me. Log base A of x1 times x2. What does that equal in terms of logs? If you are multiplying two numbers,
Add them.
okay, so what does that look like? Log base A of x1 plus log base A of x2. Okay? All right, and then we have two numbers that are divided. So what's different over there? Subtract. Okay. Now remember, you have to have the log thing first. You can't just say we have two multiplied numbers. You have to have the log of those two multiplied or divided numbers, and then that changes. It's not just like any multiplied numbers equals the log. You know that, right? Okay. And then the last one that we need to probably is log base A of x to some power. What do we do with that? Remember? Good job. So P log base A of x. Yes. There's a lot of them with that.
These are the ones that we
Yeah, there's a bunch. That's probably the change of base rule that you're thinking of.
Yes.
Okay. How about this one to change from log to exponent and back? So what is that? ln(y) equals what? In exponential form. Oh, sorry. Equals x. What does that look like? No.
It's E.
Thank you. Thank you, Riley. You're the smartest one here. Don't try to justify your wrong answers here. Thank you. I'm glad you do. All right, how does that change? Riley, let me ask you. All right. Okay. Well, I mean, you're going to go this direction or whichever direction. Okay. Sorry. I mean, that confused me in either direction. Okay. And what do we usually use? Y equals e to the x to do. Remember what's usually, yes, go living. Exponential growth and decay. Used to model, yeah. And honestly, we'll do more of this in chapter 7. The actual exponential growth and decay is way down the road, but we're just going to do derivatives now.
But I just didn't know. My pen was like. I really appreciate every time I listen to these, like the pen.
I know, it's like maddening. Listen what I'm hearing.
It was.
All right, are we good?
You're wrong.
What's going on? All right, so we got 3 more derivatives that you need to know. And really, 2 are the same. And these are the last of them.
See your nose class, please.
for gosh sakes.
They're the same thing?
Yep.
That looks okay. I'm perfectly okay with that.
Notice that LNA is down in the denominator, not in the middle.
And it's not one.
Correct. So if you have a choice to do logs or logarithms, or sorry, natural logs or logarithms, you're going to do natural logs because the derivatives are way easier, right? Okay, so we got those. Let's try some examples here. Okay, we'll start real simple. Y equals log base 4 of x. What's y prime? I'm going to use that third one right way over there. So it's 1 over x ln 4. And this is x times ln 4, in case you're wondering. I know you know that. And I'm done with it. That's it. Nice. Okay? So that's real simple. Okay.
It's going to get harder.
Yes.
Never mind.
Let's let y equals ln of x squared. Okay, so right away, what are we going to use? Chain rule. That's right. I'll let you, I'll give you a minute. You done? What'd you get? Yeah. Y prime equals ln of, if you do the u, you go like that. Sorry, that is not, that's still y. It's still y, right? Y prime 1 over x squared times 2x. X cancels, 2 over x. Okay? All right? Who's doing u in here? Nope. I did it. And you don't, you just do 1 over this, that's f prime of that, times the inside derivative of that. Okay? All right, we're going to keep going here. Let's say f of x, this is 3, equals the ln of the absolute value of 2x minus 4. Okay, so we take, if you're doing ln of u equals that. So 1 over u times 2, 1 over 2x minus 4 times 2, 2 over 2x minus 2, 2's cancel, 1 over x minus 2. Okay? If you're doing just ln of the inside, sorry, the derivative of ln is 1 over it, and again, you get the same thing.
Basically, the difference is you just
Yes. And you hopefully will get there where you don't have to spell out the U, but if it makes you feel good, I mean, it took me several years before I could get there, and I'm not even kidding. Because, yeah, I agree. It made a lot more sense. Okay, to me as well. All right, let's try. F of x is 2 ln of x minus 4. And this time, let's find f of 5 over x minus 4. The 2 is just hanging around. Derivative of 1. Then plug in 5. Get 2 over 5 minus 4, which is 2. Got it?
I didn't even do it intentionally.
What's that?
My notes are written now.
Rachel, Rainbow? If you're doing U, it would look like what? F of 2 ln of U, where U is x minus 4.
Yeah.
So that's 2, 1 over U times 1, and then you plug in, and then you're, yeah. She's all good. Okay? You like me? Right. All right. Good job. Okay. Okay, let's find the derivative, right, a little different, of ln sine of x. You got it. Remember, this is that right? Yeah. Okay, thank you. All right, so let's do f of x equals log base 10 of 2 plus sine of x. Let's find f prime of x. Yeah, f prime of x, y prime, d dx. So f prime of x, 1 over that with the addition. Be careful about this. Okay? Remember, that is in parentheses, and then times cosine of x. So cosine of x over 2 plus sine of x. And a lot of times that'll swing around front, but it doesn't matter. It's kind of it's a constant. Usually we put a constant. No biggies. Okay. Any questions on that? Got it? All right. Let's on this one, we're going to I don't want this. Let's say y is ln of x plus 1 over radical x plus 2. Now, I want you to simplify using your log rules first. So let's do that together, just so I know what I'm talking about. So we start with division, right? Well, actually, let's write this with a power. So what does that look like using your log rules? ln, what am I doing with these two? Okay. And that one has a 1/2, so we put that out front. Okay. Now go ahead and differentiate. X plus 1 times 1. X plus 2 times 1. And what do we got? And you can leave that. And again, if you're looking at multiple choice, you just did they put it together. When they're totally different, they usually don't bother. Just leave them alone. But you'll know that. And if it's free response, that's totally fine. Okay? Any questions about that? All right. So now let's talk about something called.
Why is it addition instead of?
Because we are divided. Good.
I had it written down.
And you could do, if you did it, yeah. If you did that, you would have x plus 1 times x plus 2 to the negative 1/2. And once you do the x plus 1 plus, and then that would just give you your negative when you pull it out. Oops, I got my ln. Okay. All right. This is called logarithmic differentiation. Say that 3 times quickly. Okay, that is not what we've been doing. Okay, we have been finding derivatives with logs and natural logs, but that is not logarithmic differentiation. Okay, when do we use it? Okay, when we have a this is not very scientific, a bunch of powers. Okay, it would be helpful because we can subtract instead of multiply or divide. We can add instead of multiply. Okay, and then also when we have our variable is in the base of an exponent and the exponent. Okay, and I'll give you an example. Like x to the x.
It's that's
a function. Yeah. Okay, so let's start there, and we'll go through the rules of what to do, but that's when you use it. Now, it is never going to be, except for your homework problems, they'll specifically say use logarithmic differentiation, but otherwise it's your choice. And, you know, it's an ugly equation. It's going to be ugly either way, but sometimes this makes it less ugly. Okay, so what are we on? 8? Okay, let's find differentiate y equals x to the power radical x. Okay, so we have a power x, radical x, and we have a base. Okay, so the first step in logarithmic differentiation is to take the natural logs of both sides of the equation. Okay? All right, so that gives us ln equals ln x radical x. Okay, pull it out. Let's use some
Like the pound.
Okay, so then, yes, use your log rules to simplify. Okay, so ln equals radical x goes over on the front side times ln of x, and that is multiplication. Okay, now, what do you think we should do next? We're trying to find the derivative. Differentiate both sides. And what we did is now we don't have y equals, so it will have to be implicit, sorry. Okay, so what does that look like? ln y, what's the derivative of the ln y? It's 1 over y divided by x. That's right. Did you just say that or in a different order?
I'm just. Oh, because you're not, okay, you're not, that makes sense.
Okay. All right. I reminded you of something, so what kind of rule are you going to use for the right-hand side? Product rule. Go for it, Sarah. You might want to change that to x to the 1/2. Okay, x to the 1/2 prime.
X plus x to the 1/2
Okay. Now, are we still writing out the product rule like that, or are you getting yes? Okay. Eventually, you will want to just dive right into the logarithm. I get it, and that's smart. Okay. What is the derivative of x to the 1/2? Okay. All right. So I got ln x on the top of that, right? Okay. What is the derivative of ln x, Riley? Go back a few pages. You,
Oh, 1 over.
okay. 50. All right, so 1 over x. Okay. All right. So now we just have to solve for dy dx. Okay. So let's see. The only dy dx I got here, right? Let's clean this up a little bit over here. What is, this isn't gonna, nothing's gonna happen to this. This certainly we can simplify to be what? Which is both powers of x's, okay? Or even x to the 1/2. Okay, I'm trying to make it look like the O thing because it might. All right, now, if I hit dy dx up over on the left, where's that 1? What's going to happen to 1 over y? Multiply by y. Yes.
Because to divide a function.
Right. Okay. Now, let me just say that because our fractions are very similar, let's put them together. So my common denominator is what? 2x to the 1/2? And what's my numerator, my new numerator? Good job. ln x plus 2. So I need 2. Oh, whoopsie. Okay, now, really, what's y, girls? X to the x. So put that back. There's your answer. Yep. No. Not here, no. Well, it's just a, and again, if it's multiple choice, you'll know they won't have a y hanging out here. They'll have an x radical x. So if you forget, it's just a quick, oh, yeah, I forgot to do that. But if you stop here instead of going here, you might not recognize the correct answer. Just again, if they're real close, we'll put them together. But that last one where they weren't close, usually, typically, they leave them alone because it just makes it like so much bigger and uglier. And all right, any questions about logarithmic differentiation? Okay.
I had a question.
Yes.
So I get we're really simple logs, but like, so the equation, it didn't have a log in it.
So you took the natural logs of both sides.
Decided that.
Yes, and that's
So-
totally legal. As long as you're doing
Yes.
both sides.
Yes, but then you could also decide to just do it like normally, or you do. I mean,
Could
it
you?
would be- I don't even know if you could. Or like,
I don't know about this one because what,
well, we don't. All I'm saying is, I don't.
let's see. So the original problem was x to the radical x.
I don't even know.
So x to the u, where u equals radical x.
And then
So what's the derivative here? U times,
yeah, and yeah,
ugh. Right? I'm plugging back in here. What's the matter?
I'm just, I know it goes very bad. I'm just.
Those are going to cancel each other out, right? These two. Now, is that, let me put that on double. Is that the same thing? And here's a, I mean, doesn't look the same to me. I got the 1/2. See, the problem is, if it's multiple choice, I think this is fine. It's not multiple choice. If it's multiple choice, it's going to look like this near likely. What? Where'd you get those LNs?
Yeah, I understand like what they're doing.
Yeah.
I was just wondering.
Yeah.
We created the natural.
We did. We totally did. And we'll come back to this in a minute. Let's do one more example. And again, I want to use log differentiation. Y equals sine of x over x squared plus 1. And this whole thing is squared. You need to do that? All right, you want to try it? Okay, so everybody got this. Now, the biggest mistake is this 2 doesn't get multiplied by everything. Remember, this whole thing is to the second power, so you got to make sure don't lose that 2. You can put it twice if you want. You distribute it right away, which means you're kind of doing this on that. Yeah, that was probably smart, especially if you know you're kind of prone to just some errors like that. You can put a 2 here, 2 here, and you're done. Okay. You know I'm not prone to any errors like that. Just kidding. I'm kidding. Right, Ruby. Thank you. Thank you. Okay. Now I am differentiating. Yes. Okay. All right, so this is 1 over sine times cosine, okay? Because the derivative of that, all right? And then 1 over x squared plus 1 times 2x. Okay, so 2 cosine over sine. I'm leaving them separate, which you probably did cotangent, right? Okay, what am I doing? Because I was saying tangent. Yes. Okay. I'm going to leave them separate, and then we're going to multiply by y, right? Okay. And then we're going to put that y back. So, right here.
Oh, you made it.
Cosine x, sine of x, and yes, it's okay to write cotangent if you want. Okay, minus 2x, x squared plus 1, and what was sine of x squared? Okay, so let's see if we could, now, yeah.
So would one form be?
Well, here's the problem. If you, I guess, yeah, it's a good question because how do I know what I'd rather do? I don't know that logarithmic differentiation, we did it for practice, but I don't know that it was, I mean, I took some shortcuts because here's my quotient rule, here's my chain rule, and then I just kind of put the 2. The thing I would look for is, if you are going to use logarithmic differentiation, is you should have a y kind of hanging out there. And your y, remember, was that thing right there. So,
I don't like that you can't just leave it as a one.
Well, like if you're on multiple choice,
right.
and then you look at the beginning, you're like,
Yeah. But I think it's going to be more like your logarithmic differentiation that you definitely want to use it is like with this guy right here. This is telltale logarithmic differentiation. When you got your base and your exponent to be x's. It is, when you look at it, it's like pretty nutty.
I think like if I get this, I can